All right, we're ready to start Chapter 8 now, which has to do with the Boltzmann distribution specifically. We've talked a little bit about the Boltzmann distribution. We've talked about statistics off and on in between talking about thermodynamics per se. Now, for the first time, we're really going to talk for a fairly extended period of time about the actual content of statistical mechanics. We won't be able to go very far into statistical mechanics. Statistical mechanics is really a full semester class in its own right in a lot of ways, but we can get a little bit of an introduction to it at least, to go a little bit further than we have already. I hope I've laid the background for this section by talking a little bit about how these statistics work already. So earlier, we talked about isolated systems, systems where the energy is conserved. The energy in the inside the system can't get out, energy outside the system can't get in. And we saw that for such systems, there's the ergodic hypothesis, which is the thing that allows us to do probability at all. It's the link between whatever's going on inside the system and the idea of probability. There's some necessary hypothesis or postulate or something like this that's always necessary to connect statistics to physical reality. The ergodic hypothesis says that if you have an isolated system like this, then all the states which have equal energy, and all the microstates, and all microstates must have equal energy, right? If you're in an isolated system, the energy can't change. Then they all have equal probability, and we talked a little bit about what that means. It means things are going along so complicated in such a chaotic way inside the system that every possible state gets hit, and not only gets hit, but gets hit equally likely in the course of all the fluctuatings and evolutions and stuff that are going on inside the thing. And if the ergodic hypothesis works, then the probability of finding some subset of states, S, in other words, some part of the states, not all the states, but part of them, the probability of finding some element inside that subset is equal to the number of microstates inside the subset divided by the number of microstates total, and that's just the fraction of all the possible states in subset S. That's a little abstract. We used it a little bit earlier on. We're going to basically forget about it pretty soon now. We're going to use it a little bit in what immediately follows. But this formula is true and correct, and it's the foundation for everything, but it's hard to use in any practical way. What we're going to talk about next is much easier to use and much more powerful for that reason. So we've been talking only about isolated systems so far, and now we're going to talk about a system that's in contact with a temperature bath, so heat energy can flow in and out. Not an isolated system, energy is no longer conserved, and what we want to know is what's the probability of observing any one of the microstates inside this system. So it might be an ideal gas, in which case a microstate is a collection of all the positions of the atoms and all their momenta. It might be something more complicated, in which case a microstate is also a little bit more complicated. It might even be something that we decide we want to use quantum mechanics on, in which case a microstate is a single quantum state. But whatever a microstate is, we want to know the probability of finding that microstate. And here's the answer. We're going to derive this answer and take some time deriving it now. We've seen a version of the Boltzmann distribution before, in the sense that we talked about the ratio of two probabilities, but now this is just one probability at a time. And you can see that it's related. There's something similar between these two, but there are also a little bit of differences. And so we'll go through where this came from and hopefully understand as a result. All right, so first of all, we're talking about an isolated system or an open system. Sorry, we're talking about an open system, not an isolated system. But everything we've talked about, the second law of thermodynamics, also our ergodic hypothesis, all the basic things require an isolated system. How do we deal with an open system? Well, it's easy. We just assume that the universe itself, or a significant part of it, the part that actually interacts with our system, is effectively isolated. We pretend, at least, because in truth it's a good pretense, that no energy can get in or out of the huge outer global system, and so everything is part of an isolated system. And then we consider our system per se, the thing we actually call the system, to be just one little piece or part or subsystem within a larger isolated system. And if that's true, then everything that's not part of our little subsystem is big enough to act as a temperature bath. So if energy goes out of our system or energy goes into our system, it doesn't change the temperature of the bath. It's too big. There isn't enough energy inside this little system to have any effect at all on this huge outer temperature bath. Outer surroundings is what we're going to call it from now on. So we're going to call this the surroundings from now on, and this the system, even though we're also considering it to be enclosed in a big outer system that's got isolating walls. So in that case, the total energy of the system, of the universe, is conserved. That's the U for the surroundings, the energy for the surroundings, and the energy for the system. Those two compose the entire universe here, and so that energy is conserved. And we're going to say, and this is a little bit of an approximation, but it's an extremely good one, that whatever goes on inside the system here doesn't statistically affect things that happen outside the system. Energy can flow in and out, but the actual detailed movements of what are going on inside the surroundings here aren't affected by the detailed goings-on inside the system. And in that case, the two parts of our bigger system are statistically independent, and that means that the number of microstates of the universe, of everything, the total number of microstates, is equal to the number of microstates inside the system times the number of microstates available to the surroundings. Like before, whenever I don't put a subscript on something, I'm going to consider it to be a system property. So W cis is just W because we're always talking about the system. Putting cis on everything gets to be a little clumsy. So anything that doesn't have a subscript, whenever I'm talking about the surroundings, I'll put sir on there. But whenever we're talking about the system, I just won't put anything. All right. If that's true, then the number of microstates in the system, right, no subscript, is related to the entropy of the system. And so we can say W is e to the s over kb. And that's also true for the surroundings. W for the surroundings is equal to the entropy of the surroundings divided by kb, e to the entropy of the surroundings divided by kb. We're going to assume for the moment that we know something about the number of microstates in the system. The interesting thing that we need to find out about or explore is how many microstates are available to the surroundings. This huge outer, not very well defined thing, how do we say anything about the number of microstates out there? Well, it turns out that we can. So, first of all, we use the fact that the surroundings are a temperature bath. If that's true, then the derivative, as we've seen, the derivative of the entropy of the surroundings with respect to the energy of the surroundings is equal to 1 over the temperature. But if it's a temperature bath, then that's a constant. So we can just integrate both sides of this and get that the entropy of the surroundings is equal to the energy of the surroundings divided by this constant temperature, plus some integration constant that in the end we're not going to need to know, so I'll just call it const. But if the energy of the surroundings is conserved, well, if the total energy is conserved, then the energy of the surroundings is, there's a little bit of a subtlety here, but we can say it's the same thing as minus the energy of the system. And so we can replace this energy of the surroundings with an energy of the system, except for a minus sign. And so entropy of the surroundings is equal to minus the energy for the system divided by T plus some unknown constant that we don't care about. And that means that the number of microstates available to the surroundings is equal, again, to a constant we don't care about, times E to the minus energy over kb times temperature. So here I'm just substituting this relationship up into this relationship up here. And that's where this expression comes from. This is a really important expression. And we'll see it has lots of implications. It's basically the origin of the Boltzmann distribution. You would think that when we're talking about the statistics for a system, we'd be interested in system quantities, but it turns out that the quantity we really need to know is the number of microstates in the surroundings and how those change when the system energy changes. Look what it's saying. It's saying that if the system energy goes up, if this number gets bigger, then the number of microstates in the surroundings is going down. Does that make any sense? Well, it does, right? Because if here's our system, in order for the energy of the system to get bigger, we had to take some energy from the surroundings. So when U gets bigger here, energy of the surroundings is getting smaller. We saw earlier that when the energy of anything gets smaller, the entropy also gets smaller. That means the number of microstates is also getting smaller. So this makes at least qualitative sense. And all of this logic up here is showing that it also makes quantitative sense. It's actually the correct expression. Likewise, if we go the other way, if the system loses energy itself, so that means this U is going down, that means the number of microstates is going in the surroundings is going up. And for the same reason, right? That means the surroundings is gaining energy, and therefore the number of microstates is going up in the surroundings. All right. That means that for the total number of microstates in both system and surroundings, it's going to be proportional to, leaving out this constant for now because we don't need it anymore, the number of microstates available to the system for a given energy in the system times e to the minus energy of the system over kBt. Now we're getting somewhere. We're starting to get some real expressions. The next thing we want to do is use this basic expression up here, this one, to calculate our probability in this case, because it is an isolated system. This is the expression that applies for an isolated system, right? The universe is isolated, so statistics of the universe, we can use the isolated system expressions for that. So we're going to need the total number of microstates for any energy, right? So this is the number of microstates for a specific energy inside the system, but the system can change its energy, right? It can exchange energy, so we need to know how many microstates is available when any energy is possible, and to do that we just add up all these guys over all the possible energies. So we're just adding up all the possibilities. And so we get this expression. It's the sum over all the energies of the number of microstates for each energy times e to the minus u over kBt. And that turns out to be the same thing, if you think about it for a minute, as the sum over all the microstates of the system, right? The sum over all the energies of the system times the number of microstates for each energy. That's the same thing as summing over all the microstates of the system. And so we can rewrite this Wt as being proportional to, actually, a sum of over all the microstates of the system. Actually, I'm missing a little subscript there. Of the energy for each microstate, that's the energy for microstate I, over kBt. This expression right here is very important. We'll come back to it. We'll, when it's a little bit clearer what role it's playing. All right, so let's suppose I want to know the probability of finding a particular energy of the system. According to our rule up above, that's the number of microstates of the universe for which the system has one particular energy, divided by the number of microstates of the universe for any energy. That's what we were doing up here. And that turns out to be W for everything, system and surroundings, but for a particular energy divided by all possibilities. That turns out to be this expression. And this thing in the denominator is then this canonical partition function. We'll come back to that later. And that's a good expression. There's nothing wrong with that. And in fact, we'll use this expression later on, but it's not the most important one. The most important one that we want is this probability for one microstate of the system, not for a whole set of microstates that all happen to have the same energy, but for one single microstate. That's the question we asked originally way up here. Yeah, that's the thing, that's what this expression is. let's see where that comes from. Well, in that case, if we're just looking at one microstate, then all we got to do is get rid of this W, right? Because we're not looking at how many microstates there are with a particular energy. We're just looking at one microstate, so there should be a 1 there. And that's, in fact, the answer that we get. There's the Boltzmann distribution. It's equal to E to the energy of the microstate in question. Here's microstate I, and this is its energy, divided by this quantity kBt, and in the denominator, this quantity Q. And I know that all this stuff up here is hard to follow. It would be hard for me to follow if I weren't already familiar with it. So we're going to go through this. We're going to look at a lot of examples and explore what this means, because this is a really important expression. It's the whole content for Chapter 8, and it has a lot to do with Chapter 9 as well, and with lots of things that lots of the applications that we'll look at later for this whole class. So let's begin by looking at the simplest possible example of using this Boltzmann distribution. Let's look at a case where the system in question just has 2 microstates. It doesn't have a bazillion microstates like almost every real system does. It just has 2. This is an artificial system. There aren't really cases that only have 2 microstates, or at least none that I'm aware of. But it's easy to look at. It will illuminate many things, and therefore it's always good to look at the simplest possible cases for everything when you're trying to learn about something new. So if there's only 2 microstates, then there's also only 2 energies. Our system just has 2 energies, one that we'll call state 0 and one that we'll call state 1. And energy for state 0 has energy U0, and energy for state U1 has energy U1. And so we can think of those in a sort of a quantum-ish way as just being 2 energy levels, one for U0 and one for U1. And there's some kind of energy gap between these two. If you start out in state 0 and you go up to state 1, you got to put some energy in order to do that. That's what this is. That's all of what this is saying. And now we want to use our Boltzmann distribution up here to calculate all the probabilities and quantities of interest that come from the Boltzmann distribution. So we want to know the probability of finding the system in state 0. What's the probability that we find it in this state? And we want to know what the probability is of finding it up in this state as well. And we also want to know what this denominator, this Q quantity is, this thing called the canonical partition function, which doesn't look so important right now, but will turn out to be important later. Let me just say, before we go down and actually do the calculation, what should we expect a priori? I've already pointed out that this quantity up here in the numerator comes ultimately, way up here, from the number of microstates that are in the surroundings. It's reflecting the entropy of the surroundings. So if I'm down here in the ground state, I'm going to get 1 probability, but if I go up here to the excited state, to the higher energy state, I'm going to have to pull some energy in from the surroundings to do that, right? The energy's got to come from someplace. The only place it can come from is the surroundings. So I'm going to be taking energy out of the surroundings. That's going to be reducing the entropy of the surroundings. And that's going to make this upper state less probable than this ground state is. So that's what we expect qualitatively to begin with. We expect the upper state to have lower probability than the lower state. To begin this calculation, let's start with Q, because we're going to need that, right? We need that for this formula. And we're going to need it no matter which microstate we're looking at, whether it's microstate 0 or microstate 1. We're going to need that Q for both, so let's start with that. Here's the general formula. Q is equal to the sum over all of the microstates that are available to the system of this quantity E to the energy for that microstate divided by KT. There's only 2 microstates this time. That's why we're choosing this example. It makes everything easy. There's just 2 microstates. And that means there's just 2 terms in this sum. There's the term when I is equal to 0, and there's the term when I is equal to 1. For the I equals 0 case, it's E to the 0, e to the u 0 over kBt, and for the I equals 1 case, it's e to the u1 over kBt. It will be convenient. It isn't necessary. We'll get all the right answers even if we don't do this, but it makes things simpler if we choose for the energy of the ground state, the lower energy state here, to be 0. And therefore, the energy of the upper state is just the energy of the gap between the two, so U1 is equal to delta U here. Again, that isn't necessary, and I'll talk more about this. This has to do with something called the 0-point energy issue. It's a little bit of a complication later on. But it does make things simpler, and I don't want to deal with the complications now. I want to deal with the simplest possible case. So there's our partition function. Here's that partition function when we use the fact that this energy is 0 and this energy is delta U. So it's a pretty simple expression, 1 plus e to the delta U over kBt. P0 is then, according to our definition up here, right, according to this up here, this guy right here, what we want, if we want to get P0, is put a 0 in there. So P0 should be e to the U0 divided by Q. And U0 is a 0, so e to the 0 is 1, so it's just 1 over e to the, over 1 plus e to the minus delta U over kBt. P1 is the same thing except we put a U1 in there. U1 is equal to delta U, so we get this expression. Those are not too bad as expressions go, not very complicated, but not immediately obvious what they mean either. These are our answers so far. So let's look and see what they mean a little bit. We'll do that by doing some calculations, and then we'll look at some graphs after that. First of all, we got to choose a temperature, 300 K. Choose a size for the energy gap, right? It turns out that only the energy gaps are important. The absolute values of the energy, U0 and U1 here, don't matter. That's why I was free to choose this to be 0. All that matters are the differences in energy between the two states. So I choose it to be 2.5 kilojoules per mole, 2,500 joules per mole. Notice the units. I'm using macroscopic units here, and over in our expression here, I'm using microscopic Boltzmann constant. So Boltzmann constant is 1.38 times 10 to the minus 23. It's a very tiny microscopic quantity. That's not compatible, in fact, with these units. So let's do the calculation. The quantity we need is delta U over kBt, right? That's the only quantity that appears anywhere in any of these expressions. And that's the delta U in joules divided by kb, which is 1.38 times 10 to the minus 23, times T, which is 300. We have to convert this kilojoules per mole number to just joules. That means kilojoules going to joules, that's 2,500. And that means dividing by Avogadro's number to get not joules per mole, but just joules. And if we do that and plug the numbers in, then we get 1.003 for this quantity. The fact that we're getting 1 here is significant, and I'll talk about that later. And in fact, I chose this number, 2.5 kilojoules per mole, specifically to get that value of 1. All right, that's one way to do the calculation, but there's an easier way. Instead of using energy in joules, I can use energy. I can continue to use energy in joules per mole. I can use the macroscopic quantity. Instead of using kBt here, I just convert it to RT. In other words, I multiply this denominator by Avogadro's number, and I multiply this numerator by Avogadro's number, and I get the same quantity that I should get. That's 2,500 joules per mole divided by 8.314 times 300, and that gives me 1.002. The difference here in the fourth decimal place is because I only used a 3 significant figure number here for the Boltzmann constant. And I'm using 4 significant figures here for Avogadro's number, so we've got a little bit of error in the fourth decimal place. These are the same to within the error for the numbers that I used. All right, so I'm just going to use 1.00, and I'm going to forget that fourth decimal place. Then the partition function is 1 plus e to the delta U over kBt power. Where is it? here it is. Yeah, that's our partition function. So we've got to plug this in there, and that's just a 1. And so that is 1 plus 0.37 for this e to the minus 1. So that's 1.37. The probability now of finding the system in the ground state is just 1 over Q, which is about 73%. And the probability of finding things up in the upper state, we can use this formula, which is what I did. It's e to the minus 1 now, e to the minus u1 delta u over RT, divided by Q. Or I can just use the fact that these two probabilities have to add up to 1, and so P1 is also equal to 1 minus P0 whenever there's only two states involved, right? If there were more than two states, then this relationship doesn't work anymore, but at least as long as there's only two states, I could just subtract this from 1, and I'd get the same answer. So there's about a 1/3 chance of finding it in the upper state and about a 2/3 chance of finding it in the lower state. We're going to look at what that means down here when we look at these graphs, but before we do that, let's look at two other special cases. So in this case, we were doing the calculation at 300 K, room temperature, a typical temperature, and we got 1/3 and 2/3 for our populations of our two states. Let's now look at what happens when we put temperature equal to 0. What do you expect intuitively in that case, right? Well, if we put temperature equal to 0, now there's no thermal energy out in the surroundings. It's going to get very difficult, virtually impossible, in fact, to pull any energy out of the surroundings when there's no energy out there. And so we expect to see the probability all in the ground state. There's no way to get the energy you need to get up into the upper state. And we see that in the formulas. If temperature here is 0, then this quantity, no matter how small or big this delta U is, this quantity is infinity, right? And so we've got e to the minus infinity power, that's a 0, and we just get 1 for Q. So Q has reduced itself to 1 now. For P0, then, we've got 1 over Q, and that's just a 1. And for P1, we've got e to the minus infinity over Q, and that's just a 0. There's no probability of being found up here. All the probability is being found in the ground state. That seems reasonable. Let's consider the opposite extreme, where the temperature goes as high as we like, approaching infinity. In that case, up here, this temperature is infinite. That means this whole quantity goes to 0. We've got e to the 0 power. That's just a 1. And so Q is 1 plus 1. That's 2. P0 is 1 over Q. That's a half. And then what's P1 have to be? Well, these two guys have to add up to 1. And so P1 also has to be a half. And the formulas give you that too. And that means there's equal probability of finding the system in either the upper state or the lower state. Why is that? Well, now, in contrast to the earlier case, you've got infinitely hot surroundings that can provide just as much energy as you like for no entropic cost whatsoever. And so getting from the ground state to the upper state or from the upper state back down to the ground state is just easy, and that's why both states have equal probability. All right. So those are our three calculations and our first example of doing any calculations with the Boltzmann distribution. Let's look at what happens if we plot this two-state case versus temperature. We're going to look at three different quantities here, the partition function itself, Q itself, the probability of being in the ground state, and the probability of being in the upper state. And you can see what happens as the temperature, well, when the temperature is very small down here, and also as it starts rising until it's way high. It doesn't quite go to infinity, but it gets very high. Let's look at what happens to this Q quantity, this partition function first. As the temperature goes up, it rises, and you can see that it approaches a limit here, asymptotically approaches a limit of 2. What's 2? Well, it's the number of microstates in our system. We'll see later, further down, that that's always true. The number of microstates in the system, Q becomes the number of microstates in the system when temperature goes to infinity, no matter what the system is. In this case, there's only 2 microstates, so it approaches this nice 2 value. But if we had a million microstates, it would eventually approach a million too. What happens to the ground state probability? Well, when we're at zero temperature, it's maximized, right? You can't have a probability bigger than 1, so it has nowhere to go but down from there, and that's what happens. As the temperature rises, we're starting to move some probability from the ground state up to the excited state, and so the probability of being in the ground state drops. And likewise, the probability of being in the upper state rises, and you can see that when the temperature is near 0, the probability of being in the ground state is 0, and the probability of being in the upper state, the probability of being in the upper state is 0, and the probability of being in the ground state is 1. And you can see that it remains that way for a while, right? There's a small range of temperatures here near 0 before the system kind of turns on, and you start getting some population up here in the excited state. And that's because of this energy gap. It turns out that when there's a gap like that, it's sort of a quantum effect, if you like. We haven't talked about quantum mechanics, and we won't talk about quantum mechanics in this class, but it's kind of a quantum effect. Anytime you've got an energy gap like this, that's kind of a quantum effect. Then it takes a certain amount of temperature before you start getting any significant population in here, and that's what we're seeing here. There's a little bit of a turn on at the low temperature range. All right. Also notice that as the temperature goes towards infinity, very high, both of these two probabilities approach the same value of 1/2. And that's because all states now have enough energy to be equally populated because there's lots of energy in the surroundings. Okay, now, that's our first example. We're going to do more examples in the days that are to come, and we'll see in more detail how this whole thing works. But let me make a few general observations before we move on. In fact, that'll be the end of the lecture for today. First of all, just some general notes on the nature of probabilities. All probabilities, no probability can be negative. The smallest probability you can have is 0, and no probability can be greater than 1. And the reason that no probability can be greater than 1 is that all these positive quantities have to add up to 1. The sum of all possible probabilities has to always add up to 1. So that's just a few general properties of all probabilities, and since Boltzmann probabilities are probabilities, it applies to them too. It applies to every other kind of probability too. This is a point I already made, namely that this Boltzmann exponential term, this energy divided by RT here, or kBT, depending on what units energy is in, that comes from the number of microstates in the surroundings, and it's reflecting or taking account, keeping track of what's going on in the surroundings. This exponential term isn't keeping track of what's going on in the system. It's keeping track of what's going on in the surroundings. It's taking account of the fact that when you take energy out of the surroundings, probability should go down, and when you put energy into the surroundings, probability should go up. And that's all I'm saying here. I really said all these things before, so I won't repeat them now. The next thing to say is that the only quantity that appears in the Boltzmann distribution is the energy gap in units, or scaled by, this quantity RT, or kBT if you're using microscopic units. This is in macroscopic per mole units. And I'm going to tend to use these per mole units because they're way more convenient. But remember that in reality we should be using the microscopic units because this really is a microscopic theory. But you can get away with using the per mole units, which are more convenient, pretty much always by being consistent with the units, right? If you use per mole units for delta U and per mole units down here, then you'll get the right answer. All right. And that means, therefore, that this is the only quantity that matters. If this quantity is much smaller than 1, then that means you've got exponential to a very small quantity, something near 0, which is always around 1, which means you're in a situation where everything has more or less equal probability. In the two-state system, that's true, but it's also true if you've got a whole lot of other states. Once the energy is high enough, once delta U is approaching once delta U over RT is approaching 0, then all the states get populated. If delta U is over RT is much, much greater than 1, that means the energy gap is much bigger than the available energy. Then the exponential is e to the big, whatever big happens to be, and that's going to be e to the minus big, and that's going to be approximately 0. That means all the population is going to be in the lower energy states, or even in just the ground state alone, depending on how big this first energy gap is. And we already looked at the case where delta U over RT is about equal to 1. And that's the case where you've got sort of a range of reasonable probabilities for the first few states as long as delta U is not too big. All right. And so, just to make the general point, this quantity RT, or KBT in microscopic units, is the relevant energy scale for everything. If you want to know whether an energy is big or small, compare it to KT, or to RT. If it's small compared to RT, then it's not a very big energy. If it's big compared to RT, then it is a big energy and will have a big effect. Yes, at T equals 300, it depends on temperature, obviously, right? So how big the energy scale is depends on what the temperature is, but most of the time we're at 300. In that case, the quantity RT is 2494. We did that calculation earlier because it showed up in thermodynamics also, right? Now it's showing up in statistical mechanics, and for the same reasons. I mean, stat mech and thermo are really part of one big giant statistical, macroscopic thermodynamic theory. And so we're seeing the same relevant quantities in both of them, and for temperature near 300, 2494 is a good number to remember. Okay, point number 5. When the temperature approaches infinity, then I said this earlier, the partition function Q approaches the number of microstates available in the system. If there's only 2 states in the system, then it'll approach 2. But if there's 100 states in the system, it'll approach 100. And if there's Avogadro's number of states in the system, as there usually is, in fact, then it'll approach Avogadro's number. Whatever W happens to be, however many microstates, that's the number it will approach as the temperature gets high enough. Let's see why. Here's the definition of Q. It's the sum of this Boltzmann exponential over all the microstates in the system. As temperature goes to infinity, all these guys go to 0, and all the Boltzmann exponentials become 1s, and we're summing over all the states in the system, so it's just W. So mathematically, it's easy to see how that comes about, but it has large implications. That may seem kind of like a coincidence to you, but it's not a coincidence. We will see, in fact, that this Q quantity plays a role that's very similar to W for an open system. So for an open system, and this is for an isolated system, these two guys play largely the same role. All right, so for low temperature, where the first energy gap between the 2 lowest states is already much bigger than RT, Q is just 1 because everything's frozen in the ground state. For an intermediate temperature, where the energy available in the surroundings is RT, that is similar or the same as delta U, then the first few microstates are populated. And when the temperature gets really high, higher than even the highest of the microstate energies, then all the states will be roughly equally populated. That's what the Boltzmann distribution roughly is saying. I said this before, let me just finish by saying it again. I said it just above, that earlier we saw the Boltzmann relationship, right? The entropy is just basically the log of the number of microstates available. We will see in chapter 9 that something called the Helmholtz free energy, A, is the log, essentially the log of the partition function. The Helmholtz free energy is, for an open system, plays the same role as entropy plays for an isolated system. So the Helmholtz free energy is in some ways equivalent to the entropy, but we have to talk about that a lot more before that will become clear. Both of them, if you know them as a function of the relevant variables, will give you all of the thermodynamic properties for the system. So these guys are extremely important because they represent all there is to know about your statistical or thermodynamic system. And therefore, they're the targets and goals of many thermodynamic and statistical calculations. Final thing to say, statistical mechanics can predict all of thermodynamics from the microscopic properties of the system. That's the subject really of Chapter 9, and we'll get there.